right, we're going through our carboxylic acid derivatives in order of their reactivity. So the most reactive being acid chlorides, then anhydrides. And in similar reactivity level, we had carboxylic acids and esters. We're going to start out with carboxylic acids. So say we wanted to take a carboxylic acid and maybe turn it into some other carboxylic acid derivative. In this case, I just have a generic nucleophile there, but essentially we could change that out for a specific one if we wanted to. So say we want an ester, so maybe we're changing this into the methyl ester, so there's just an OCH3 there. If that was the case, we'd have our nucleophile here would be OCH3 minus, and what is going to happen under these conditions, I guess, is what you should be thinking about. When we react OCH3 minus, or a strong nucleophile, with a carboxylic acid, what happens? Does it add to the carbonyl carbon? Is there something else that it can add to? And hopefully this is really jogging your memory for something we learned about in the Grignard organolithiate chapter. And essentially what we learned there was that if we have a really strongly acidic proton, or even a moderately, in this case a pretty strongly acidic proton, a carboxylic acid proton, and a strong nucleophile, acid-base chemistry is going to take precedent over addition chemistry. Acid-base chemistry has really low activation energy barriers, and this is a pretty acidic proton, right? We have a pKa of a carboxylic acid around 5. So if we added, let's say, OCH3 to this, instead of it adding to the carbonyl, it's actually just going to add to that hydrogen, resulting in a proton transfer with a carboxylate plus an alcohol. And that alcohol, remember, has a pKa of around 16. So this is a very favorable reaction in the forward sense. So can we turn a carboxylic acid directly into an ester under basic conditions? This is a base right here. And the answer is no, because strong nucleophiles are also strong bases. And that's what we talked about a lot during that organometallic chapter with Grignards and organolithiates. We had to use only aprotic solvents during any of those reactions because the nucleophiles would also just act as bases and deprotonate. So this might be our desired product, but using basic conditions to get there will not produce any of that desired product. Instead, we're just going to get an acid-base transfer. So that's a little bit of a challenge with these carboxylic acids. How are we going to do it then? Well, to react a carboxylic acid as an electrophile, the reaction must be under, this is basic conditions, we're going to do it under acidic conditions. So there's going to be some strong acid in solution with our nucleophile. We're going to see that in a moment. So we just said we had to be under acidic conditions, not basic conditions, for a carboxylic acid to react as an electrophile. So that's what we have here. We have sulfuric acid as our acid catalyst. We have an alcohol that is going to act as a nucleophile. We can see that the OCH3 is in the product. We have our carboxylic acid, and we have water on that side. So what we want to first think about is just, is this reaction favored? Is it neutral, or is it disfavored? So pause the video and think about that for a second. Think about what factors we would want to look at to decide on that. All right, so what factors are involved in if it's favored or not? Enthalpy and entropy, so delta H and delta S. So let's hit the easy one first, entropy. Do we have more molecules on the left or on the right, or the same amount? Well, it's 2 molecules over here going to 2 molecules over there, so entropy should be pretty much neutral. So that's not going to impact if this is a favored or disfavored reaction. What about enthalpy? Enthalpy is all about the bond energies, right? So what bonds are formed, which bonds are broken? And what we have to remember is this is nucleophilic acyl substitution. So this whole piece is replacing this piece right here. So what's happening? Well, we're breaking a CO bond. So the bonds we're breaking include a CO sigma bond. What about this? Well, this piece is being added there, and in the process, the oxygen here used to have a hydrogen. It's gone now, so we also broke an OH sigma bond. What bonds were formed? Well, we broke this CO bond, but we formed this CO bond. So CO sigma bond was formed. And then what else did we form? Well, this OH just had one H, and now it has two H's, so we formed an HO sigma bond. So is this favored or disfavored as far as the enthalpy? Well, we broke that, we formed it. We broke that, we formed it. Same bonds are being broken and formed. So this is a pretty neutral reaction. So in a reaction where both sides are pretty much the same energy, what is going to force it one direction or the other direction? Hopefully you're thinking about back to kind of the acetal stuff that we learned about previously. How did we force an equilibrium forward when we were forming an acetal? We did it by having an excess of a given reagent. So one of the blanks on the bottom of this page of the course notes says in Fischer esterification, so this reaction is called a Fischer esterification, an excess of blank is used to drive the reaction to completion, Le Chatelier's principle. So what would we use an excess of to push this in the forward direction? Yeah, if we have an excess of this alcohol, that pushes the reaction in the forward direction. So if we're running an esterification reaction where we are taking a carboxylic acid, turning it into an ester, we're going to use an excess of this alcohol to push that reaction forward. How does the mechanism work? That's where we're going next. Okay, how does this reaction work mechanistically? How can we rationalize that it pushes forward a product using our mechanistic thinking? Okay, well, we have our acid catalyst, our sulfuric acid around. So we'll draw that right here. Yeah, that's fine. So we'll just draw a bond from that O to H, because somehow we're going to have this proton being transferred. It's the acid catalyst. And what can that transfer to? Well, it could transfer to that oxygen, to that oxygen, to that oxygen, but which of these is going to be the most electron rich of all those oxygen atoms? And we know that we can pull electron density up to that oxygen from that carbonyl. And one thing we talked about in chapter 19, the carboxylic acid chapter, was, well, which of these oxygens is more basic? Is it this oxygen or this oxygen? And what we found is that when we protonate this oxygen, we have greater delocalization of the resulting positive charge, and that makes it more basic. And that's what happens. So to move this reaction forward, the first thing that happens is this oxygen is going to protonate. So that will form this species here. And essentially, why do we have to make this species occur before this alcohol can add into that carbonyl carbon? Well, essentially, this carbonyl carbon has some partial positive, but the partial positive is going to become greater. It's going to become a stronger electrophile once we protonate that oxygen, because we can draw other resonance structures that seem to have more merit. We can draw a resonance structure where we pull those electrons up, making the R, making that carbon bear a full positive charge. We can do the same thing here, but if we did it up there, then that oxygen would have a negative charge. And here, it's neutral, and we know that oxygen would want to be neutral. So this is now a stronger electrophile, and this rather kind of weak nucleophile, weak base that we have isn't strong enough to add to a kind of weak electrophile. It needs a strong electrophile. So once that occurs, this oxygen can add into that carbon. We could have shown it adding there while that simultaneously moved up, but I wanted to show the resonance structure first to see why this is a stronger electrophile now. So once that occurs, and I guess one thing I didn't do here that I should have is all of these steps are technically equilibrium steps, right? Because we said the products aren't really any more stable than the reactants. So this is being driven by equilibrium. We're adding a lot of this, and that's pushing it forward, but each of the individual steps is in equilibrium. Is this step in equilibrium? No, right? Because resonance structures are not in equilibrium, they all simultaneously exist. So make sure you understand that difference as well. Okay, so that added in there, that makes this intermediate here. And either of these oxygens could theoretically swing their electrons down. This is our tetrahedral intermediate. We'll keep this one being the one that would swing its electrons down, just to keep it kind of in the same place. But if the electrons came down right now, this would be the best leaving group. So if they came back down now to reform the carbonyl, the best leaving group would be this, and it would transfer back up to that intermediate. But this proton is going to transfer between all the different species in solution. It can also transfer intramolecularly to that oxygen right there. Which side of this equilibrium is favored? Neither, right? We have essentially oxygen with 3 carbons around it and a positive charge. Here's oxygen with 3 bonds around it and a positive charge. This is also oxygen with 3 bonds around it and a positive charge. So again, both sides are pretty much equal, so that transfer is going to be really low activation energy, and both of those species are going to be in equilibrium. So at this point, if the electrons swing down from here, the best leaving group is now the water molecule. So those electrons can come down, reforming that carbonyl, kicking out the OH2. That would produce the water molecule plus that species right there, the pretty much ester precursor. Just need to deprotonate that oxonium ion. And at this point, water could do that deprotonation. A methanol molecule could do that deprotonation. The conjugate base of sulfuric acid could do that deprotonation. All of them probably would if they just come in contact with it. There technically probably is more of the methanol than anything else around. So that's what I would draw doing the deprotonation. So that would be the last step. Also an equilibrium step. This is also an equilibrium step. But the key thing here is that we have so much of this around that it's going to be pushing that equilibrium forward. So that is how the Fischer esterification works mechanistically. Essentially, it's a lot of just oxonium ion turns to oxonium ion, turns to oxonium ion, till we get to the final product, right? We have an oxonium ion here. Then the nucleophile adds in. Then this is an oxonium ion. We get a proton transfer. So this was the oxonium ion. Now this is the oxonium ion. Then we reform our carbonyl from our tetrahedral intermediate. That puts that back as the oxonium ion. And then we're going to protonate something. And this technically would then be an oxonium ion as well. So it's just a bunch of that same energy reactant. All of those are going to be high energy species, but they're all similar in energy. That's just how the reaction moves forward. What didn't we have in this reaction mechanism? We have no O minuses in this reaction mechanism, right? If we had O minuses, if we had OH minus, what would happen? It would just deprotonate that carboxylic acid, and that would shut the reaction down. That's what we talked about earlier in the video. nucleophiles, bases, can't be present in this type of reaction because they'll shut the reaction down by simply deprotonating that carboxylic acid. So Fischer esterification will not proceed under basic conditions. So we have to use methanol and an acid catalyst. We can't use methanol and a base to promote this. Okay.